My name is Dr. Matthew Michael. I'm a lecturer of mathematics at NGIT. So I've been talking about differential equations, and I'm using a lot of the material out of the 10th edition of the Boyce and Prima textbook. I'm using their PowerPoints because they follow so closely to the textbook. And so I'm using this so I can help teach my students, and hopefully others, how to look at their textbook and learn from it. And so you can kind of see what the important things are and the not so important things are. So let's take a look at section 2.5. We're going to talk about autonomous equations. So an autonomous equation is an equation which is only dependent on the dependent variable. So if I'm solving for a function of y, only derivatives of y and y itself are allowed in the differential equation. We've used these, so we like these equations for direction fields a lot. So an example is a Malthusian exponential growth problem. So in this case, r is equal to positive because it's exponential growth, right? And so dy dt is equal to r times y. So the solution is very basic, just like the model is very basic. Y is equal to y naught e to rt, where y naught is your initial starting position. So it's very simple, but notice there's only y's. The only time dt shows up at all is as the differential, and I'm okay with that. But it's weak, you know. Yeah, the exponential is really useful, but how many cases do we deal with actual unlimited growth? I mean, if you throw bunnies out into the wilderness, yeah, at first the bunnies are going to go crazy breeding, but eventually they're going to start to reach a kind of stable equilibrium. They're going to reach a point where the population's going to be fairly predictable. It'll stay at roughly the same value. So what we're going to want is a model that follows this kind of motion, and we like this model, the Verhulst or logistic equation, that describes it. So instead of a constant rate function r, we're going to call it a function h of y. It's because when y is like 0, it's going to act like an exponential growth. You start off with a very small population, you toss them out in a wide open and bountiful harvest. Yeah, of course the population is going to grow. You throw a couple of bacteria in a petri dish, it's going to go nuts. But as that bacteria grows, as that population starts eating, they're going to start having to compete for space. They're going to have to compete for nutrients and where to sleep, or where to actually grow. So as that happens, the rate of growth will also decay and eventually grow to 0. And in fact, if it overreaches at a certain point, if it goes above this population cap, as it were, well, it's going to start decaying, right? If you are too big for your resources, your population's going to have to shrink. And so one of the easiest versions of this is r minus ay is equal to my rate function h of y. Plug this in and factor out an r, well, we get what's known as k, which is r over a. And if r is considered the growth rate, k is represented as the carrying capacity. It's that stable population value. So on your direction field, you'll see this as like a straight line, straight across, and that the populations are all pointing right to it. This is the value where the population goes, yeah, we like it, just like this. And so this is a direction field when r is equal to 1 and k is equal to 10. You can see that if I have a positive population, which, okay, as long as you're not extinct, you're going to reach this value of 10. But let's say we're doing something really weird. Notice that if I do plug in y is equal to 0, the population doesn't change. So technically it is at equilibrium there as well. But this is like the case where you hold a pencil above your finger. Yes, it is possible to balance out the force of gravity perfectly, so the pencil stays perfectly above your finger. But if you accidentally move your hand to the right or left, which is bound to happen, the pencil is going to eventually fall over, because this equilibrium is described as unstable. Its ground is unstable. It's why Jenga is so much fun, because it has an unstable equilibrium point. Whereas at y is equal to 10, it's asymptotically stable. The opposite, that as I move forward in time, any nudges, any movements from left to right, what if the bunnies give birth to 2 bunnies rather than 1, and it goes over the population cap? Oh no, everybody's going to die. Not. It's just going to say in the next round, you're going to have a little bit of a decay in population. Just all the nudges kind of cancel out around an asymptotically stable equilibrium. Whereas an unstable equilibrium, as soon as you're outside that range, as soon as you're not equal to that y value, it takes off, either in the positive or negative direction. And these y values can be found by looking at the rate function f. It can be described as your critical points, the points when the derivative is equal to 0. And so it's also sometimes useful to use this sketch, or to be able to understand what one of these sketches look like. Right? So taking a look at my rate function here on the left, you're seeing that, look, there's 2 y's multiplied together. That's a quadratic. And there's a negative sign here. So that's a negative quadratic. Okay? Well, y is equal to 0 is obviously 1. So let's start there. And it's negative quadratic. So, okay. It's going to have positive. So it goes up and down. Whatever value this is, which happens to be k, will be another one of those zeros. And so according to this setup, this understanding, those zeros will be my equilibrium points. Wherever the graph touches the y-axis here, and by y-axis I mean this dependent variable y, those are going to be those places which have equilibrium values. Now, everywhere where there isn't a 0, you can draw an arrow. So remember, f of y is itself a change in y. It's saying, hey, if f of y is positive, that means y is increasing. So draw an arrow in the increasing y direction. And if y is negative, if f of y is negative, that means y is decreasing. So notice all the arrows are pointing towards k and away from 0. So hence unstable and stable. We can even find a maximum growth. You can see where that maximum growth is occurring. What it actually means, we don't always need to know. But the more we can know and understand what's going on, the better we are. Another thing that you might hear from time to time is that if we just consider this axis, which y is sitting on, oftentimes we'll call it the phase line, because it's describing the different values of y and how it is acting and interacting together. If we create graphs of this, like on a direction field, or just take a look at starting points here, 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 we're going to get solutions that converge to the limiting capacity, carrying capacity, K. Unless if you start perfectly on 0, then it's going to stay on 0, of course. One thing that is really key to notice, though, so you're going to want to be able to describe what's going on in the different regions, right? So if I have equilibrium at 0 and at k, well, what's happening to the graph if I start off above that k value? Well, if I am starting between the equilibrium, what's happening? If I'm starting below the 0 equilibrium, what's happening? Being able to describe these things, whether I'm talking about concavity, whether I'm just talking about curve sketching in general, this really helps me understand what is going on. And the more I understand about what's going on, hence why I care about the maximum, the more I can help guide how my solution is going to look. can also find and solve this logistic model using partial fraction decomposition. One thing to note is that a isn't equal to y over k, it's equal to 1 over k. See? 1 over k here. Just a simple typo. So, but it's in math type, so I can't change it for you. Sorry. So using partial fraction decomposition, integrating, and using the logarithmic rule, notice these are logs, so positive log, negative log, positive log, negative log, so we have this as a fraction, we can actually solve for y. And once I plug in your initial condition, you can actually see an equation. Notice this is constant, this is constant, this is constant. The only thing changes is here. As t goes to infinity, this exponential goes to 0. And I get y naught over k, y naught k over y naught, or just k. Also notice we're assuming a y naught value lower than k. If this is not true, if I'm choosing a y naught above k, there's just a couple of things you're going to have to need to modify. It will still work out the same, but you have to be really careful about what's going on here. Make sure you don't get any natural logs of negative numbers. You just have to make a couple of modifications. See, it can be shown that the solution is also valid for y naught greater than k. You just have to make a couple of modifications. And as we predicted, asymptotically it goes to that 0. So it doesn't matter whether we use direction fields, we use those different diagrams like the phase line, or the f of y versus y. All these help guide us towards a basic understanding of what's going on. And here's an example of us actually plugging in the numbers. Another interesting variant of the carrying capacity logistic model is the threshold equation. Notice this fits everything other than we have a t and a negative sign, because the t is talking about a threshold. So this is sort of like describing, hey look, I am running a business. If I don't invest enough money in it, I'm going to eventually go bankrupt. The business will fail. But if I invest enough money in it, I'm going to make a lot of money. So if I'm above the threshold, I make money. If I'm below, I'm going to eventually decay and lose a lot of money. And by drawing this diagram, I can actually see really easily where am I losing the most amount of money and when can I gain the most. So just like the carrying capacity, I can determine threshold values and create equations like this and solve equations to see what's going on. Another thing we can do is we can merge a logistic growth with a threshold. This is the kind of logical extension of my business model. Yeah, if you invest enough money, you're going to be successful. Probably, maybe, who knows. But it makes sense that you're not going to make infinite amount of money. No. I mean, even if you're Build-A-Bear Workshop and, hey, look, suddenly we're making lots of money because lots of people like stuffed teddy bears. Well, eventually you're going to reach oversaturation. Eventually you're going to reach a point where you can't make more money than that. There's only so many people who want teddy bears. And so we will end up reaching a kind of nice place where, hey, I'm making lots of money, but I'm not an unstable. Hey, look, I invested enough money, so I made it over this threshold. So here's that modification. Notice there's still the negative sign, which kind of plays with this a little bit here. And if I draw out these models with concavity and other techniques, notice on the direction field, we have a threshold here. So it's above going to stable capacity of k or a stable capacity of 0. And notice this is a stable point now because this threshold is highly unstable.